Welcome everyone. Let's begin our lesson for today by going over the learning goals and success criteria. First, what are we learning? We're learning how to recognize patterns in the graphs of linear functions, how to find function values of linear functions, how to understand complex numbers and how they are typically represented, how to plot complex numbers on the complex plane, how to find the conjugate of complex numbers, how to simplify complex numbers and perform mathematical operations on complex numbers, how to recognize operations on complex numbers as transformations of the original complex number, how to convert Cartesian form of a complex number into polar form, how to convert the Cartesian form of a complex number into trigonometric form, how to compare and contrast mathematical techniques in order to solve complex problems, how to evaluate your options when solving problems in order to solve problems in the simplest and most effective way possible, how to find real roots of real numbers, how to find complex roots of real and complex numbers, and how to recognize closure of number sets within the number system under more mathematical operations. How are we learning it? Through the Need for Speed assignment and the Reasoning with Complex Numbers review notes and the Reasoning with Complex Numbers review assignment. When can we use this information? To determine how long it would take to save up enough money for a down payment on a car, to determine the amount of voltage used in your house at different times of the year, to look at difficult situations in your life and evaluate your options and opportunities in order to make the best decision for your life, and to perform simple calculations such as a budget by recognizing boundaries of numbers to determine if adding the items in your budget will stay within your income amount. How do you know you learned it? By getting a score of 4 on the Need for Speed assignment and a 4 on the Reasoning with Complex Numbers review assignment. Now let's take a look at our agenda for today. We will begin by going over the learning goals and success criteria. While we do that, you'll fill out your Get It Started. Once you've completed your Get It Started, we'll go over it together and answer any questions that you may have. After that, I'll give you time to complete the Need for Speed assignment on Google Slides and Google Forms. Once you've completed the assignment, we'll go over it together and answer any questions that you may have. As we get towards the end of class, we'll go over your homework for tonight, which is the Reasoning with Complex Numbers review. At the end of class, we'll go back over our learning goals and success criteria while you fill out your Before You Go. Your homework for tonight is to complete the Reasoning with Complex Numbers review assignment and any incomplete assignments that you may have. Let's take a look now at the Reasoning with Complex Numbers review notes. The notes begin with the learning goals and success criteria. Now, what is a complex number? A complex number is any number that cannot be found on the real number line. All complex numbers can be written as the sum of a real number and a complex number. So when we write it that way, it is called Cartesian form. So this is the standard form for writing a complex number. And it looks like this, a plus bi. Now a and b should both be real numbers. And then I obviously stands for imaginary. So we have our imaginary number here. And we can have multiples of them. So we could have 4i, which means there's 4 imaginary numbers. So we can look anything like this. A represents a real constant. B represents the real coefficient of I. And I represents the square root of -1. Now, from that, we can find a conjugate. So remember, the Cartesian form is a plus bi. The conjugate is always going to be the opposite sign of the bi part. So this would be a plus bi, so the conjugate would be a minus bi. Now if this was already negative, then it would become plus bi. So we always do the opposite. Types of graphs. We have the Cartesian plane, which looks like this. We have our x and our y, just like we always did. That's what we're used to seeing forever. Now, the complex plane, or as we call it, the Argand diagram, looks a little bit different. So all of this looks the same, except now this axis is called the reals, and this axis here is called the imaginary. So we would plot our real over here, and our imaginary goes up and down. So if we were to graph -2 minus 3i, well, first we need to pick out what our real number is. Our real number is -2. And our imaginary number is -3i. So now we're going to plot this. So we have our real axis here, and this one should be our imaginary axis. So our real is -2. So along the reals, we're going to go to the left 2. And our imaginary is -3. So we're going to go down 1, 2, 3. and plot our point. So this is how we graph complex numbers on the R-GAN diagram. Now we can do a few more. So we have -2 plus 3i. So we're going to go to the left 2 and up 3. And there's A. Now B just says -2i. Well, that means there's no reals, so we're not going to slide side to side at all. And my imaginary is -2, so I'm just going to go down 2 and plot that point. There's B. Now C is 4. So notice my reals is 4, but I have nothing for my imaginary, so it just goes right there. There's C. And then 5 plus 3i, so I'm going to go to the right 5, and then up 3, and there's D. So this is how we plot points on the complex plane. There's a video here as well that shows you how to plot complex numbers in Desmos, so you can go ahead and watch that video. Let's talk now about how we can plot complex numbers on the coordinate plane using Desmos. So what we're going to do is we're going to go to desmos.com and we're going to click on Graphing Calculator. And notice it gives us a standard graph, and we need to change this to become an R-GAN diagram. So what we're going to do is we're going to click on the little wrench here, and for my x-axis I'm going to label that RE for real, and y-axis we're going to label that IM for imaginary. Now we have our real and imaginary axes. Now let's say we were trying to plot the point 3 plus 2i. So let's say that's what we're trying to plot. Well, what we're going to do is we're going to treat the first number, the real number, as our x, and the imaginary number, the number in front of the I, as our y. So what we would do is we'd go ahead and put it in parentheses. We put 3, because that's our x, and then our y, which is 2, comma 2. And then we can label it. And now we have a graph with, this is 3 and 2i on the complex plane. So that's how you graph and check your work for plotting complex numbers on the complex plane. Now, how do we write these numbers in Cartesian form? Well, we have here 3 plus 5i over 1 minus I. Well, in order for it to be in Cartesian form, the denominator can't exist. All right, we need to get rid of that denominator. So in order to do that, what we're going to do is we're going to multiply by the conjugate. So if we multiply both the top and the bottom by the conjugate, we end up with 3 plus 5i times 1 plus I, and then 1 minus I times 1 plus I. And when we do that, we should see that when we multiply this, 3 times 1 is 3, 3 times I is 3i, 5i times 1 is 5i, and then 5i times I is just -5. So we end up with 3 minus 5, which is -2, and we end up with 3i plus 5i, which is 8i. So that we end up with that. Then we do the denominator. Now notice this is really a difference of squares now. So when we multiply this out, we say this is really 1 squared, which is 1, and I squared, which is -1, so it's 1 minus -1, which is 2. So we end up with -2 plus 8i over 2. Well, we should notice that 2 goes into both of these. So when we do that, we get -2 divided by 2 is -1, and 8i divided by 2 is 4i. So we end up with -1 plus 4i. So anytime we're asked to find Cartesian form, we're going to multiply both top and bottom by the conjugate of the denominator. So now what if we had something like this? 3 plus 5i times 1 plus I. Well, all we need to do is just combine those and see what we get. So we get 3 times 1, which is 3, and 3 times I, which is 3i. Then we get 5i times 1, and 5i times I. So we end up with 3 plus 3i plus 5i plus 5i squared. Well, now we just combine like terms. So we have 3 plus 5i plus 3i plus 5i squared. And we get 3 plus 8i plus 5i squared. Now I squared is really just -1. So that's really 5 times -1, which is -5. Now we can combine these, so we get 3 minus 5, which is negative 2, plus 8i. Now complex number proofs. It says choose any two complex numbers, z1 and z2, and prove that the following statements are true. So we're asked if z1 plus z bar, and remember z bar means the conjugate. So we're saying that a number plus its conjugate and another number plus its conjugate. And we're saying that those are both real numbers when you add them up. So if we do this, let's check. So we have a plus bi plus a minus bi, right? Because all we're going to do is add the conjugates together. Well, we should notice that a plus a is left, and then we have bi minus bi, so those cancel each other out. So all we're left with is a plus a, which is 2a, and that is a real number because there's no i's left. So we were able to prove it that way. So that's true. Now let's try it for the second one. So for z2, we can say c plus di plus c minus di. And again, when we do that, when we combine these, the di's cancel out, and we're just left with 2c. So this was also true. So we can see that no matter how we do this, we're going to end up with a true statement. There's a video here that shows you how to check complex calculations using Desmos. So you can check to see if your conversion to Cartesian form was done correctly. So you can go ahead and watch that video. Let's talk now about how we can use the Desmos to check our work when dealing with calculations on complex numbers. So let's go ahead and go to the graphing calculator. I'm going to go to Desmos.com, and I'm going to click on graphing calculator. And let's say that I wanted to add two complex numbers together. So 3 plus 3i plus, and then let's go 2 minus 4i. And I wanted to add those two complex numbers together. Well, when I add them together, I can do that, and I get 3 plus 2 is 5, and 3i plus minus 4i is negative I. So that's what I think it should be. So I'm going to just go ahead and put that in here for now. I think it should be 5 minus I. Well, we can check our work by putting it in coordinate form. So we have our 3 plus 2, comma, and then our second part, which is 3 minus 4, right there. So all we did was place that in there. We added the reals, and then we added the imaginary numbers, and we placed them here. And if we label this, we see that it's at 5, negative 1, which is the same thing we have here, 5 and negative 1i. Now we could also do this with subtraction. So if we subtracted these instead, now we get 3 minus 2, which we think is 1, and 3i minus negative 4i, which we think should be 7i. Now we can place that in here. So this becomes 3 minus 2 and 3 minus negative 4. And when we do that, we know that 3 minus negative 4 becomes 3 plus 4, right? And now we can check our work. So we're going to go ahead and create a coordinate. So this is 3 minus 2, comma. And then we have 3 minus negative 4, which is plus 4, which is up here. And we can see that it's at 1, 7, which is exactly the same thing we got here. So this is how you can use Desmos to check your work when adding or subtracting with complex numbers. Introduction to transformations. So we're going to look at z being some point on the Cartesian plane as 2 plus I. It says find the result of z plus 3 minus 2i. So what I'm going to do is I'm going to take 2 plus I and add it to 3 minus 2i. So I'm going to combine like terms. So I have 2 plus 3 and I minus 2i. So I just kind of rearrange it and then go ahead and bring them together. So 2 plus 3 is 5 and I minus 2i is negative I. So I get 5 minus I. And what we should notice as we go through this assignment is that this is a transformation of this one here. So just a reminder of the different types of transformations. A reflection is a flip over a line, so it's going to flip over. Translation is a slide, so we're going to take it and slide it around. Rotation means it spins, and dilation or scaling means that we're going to make it either bigger or smaller. So here's a reflection. So you can see here's our reflection. We have our triangle here, and it flips over and goes this way. We also have Simba here showing you what a reflection is as he looks into and sees himself in the water. Translation is a slide movement. So we have a triangle here and we slide it over and to the right and it becomes this one. Kind of like the players on Remember the Titans here that are sliding and moving around. Rotation, okay, is a spin movement. So we have our triangle here. If we spin it around, it becomes this one. Kind of like Woody's head does right here. And dilation means we're going to get bigger or smaller. So we have a triangle here and it gets bigger. Kind of like Bugs here. Drinks the special stuff and becomes this big buff bunny. Now, here's what your assignment's actually going to look like today. So we're going to fill in this table. So we're given 3 different z's and we're asked to perform these different transformations on them. So in this one, we're going to add a vector. We're going to add something to it. In this one, we're going to subtract. We're going to multiply by 2. We're going to multiply by -1. We're going to multiply by -3. And we're going to take the conjugate. This is z bar here. So we're going to find the conjugate of each one. Cartesian form and Argand diagram. So a Cartesian form is the sum of the real and the imaginary values. It should look something like this, a plus bi. So if it's not already in that form, we need to convert it to that form so that it looks like that. The Argand diagram is the graph of what this looks like. So we have the reals here and the imaginary here. So we would take the a value and move it over here and slide either to the left or to the right. And then we would take the b value and go up or down. And we'd plot it just like it was a coordinate on the coordinate plane. Now, polar form includes 2 components. The r value, which is the radius. Basically, we're looking at the distance from the center of the Argand diagram to the point that we've created. So that's the radius. And then the second part is the direction. So how far did we turn? Where did we rotate on the Argand diagram to get there? So for instance, we have polar form. We have a point right here, and we want to know where it's located. Well, we should be able to see that the distance from here to here is 1, 2, 3, 4. So that's my distance. So that's r. And then theta is the rotation. So I start here, and I rotated 90 degrees to get here. Notice every time we move from one box to another, that's 90. So this is a 90 degrees. So r is 4. Theta is 90 degrees. Now what happens if it's not as simple as being on an axis? Well, most of the time we then need to use our special right triangles to find the polar form. So we have 30, 60, 90 triangles. And the 30-degree angle has a distance of 1. The 60-degree angle has a distance of square root of 3. And the 90-degree angle would have a distance of 2, which it doesn't really matter here. So 30-degree angle is 1, 60-degree angle is square root of 3. Now for a 45, 45, 90 triangle, the 45-degree angle has a side length of square root of 2. So we have our Argand diagram here. This is 90, this is 180, this is 270. Now from that, we could break this up. Let's say that this is 45, 135, 225, and 315. So let's say that our point was somewhere out here. Therefore, we would say that our R value is 315 degrees because we always rotate all the way around to that point. So this is 315 degrees. So we can use 45 degrees as a reference angle anywhere on the Argand diagram to help find R. We could also use 30-degree angles or 60-degree angles as well. So for instance, we have a point here that's at 1 square root of 3. So this is negative 1 plus square root of 3i, and we want to find the polar form. So we should recognize that we can draw a triangle here. So we draw a line. This represents our radius. So from 0 to here. Well, we should notice that this is negative 1 and this is square root of 3. So we know that this is a 60-degree angle here because it follows a pattern of 1 square root of 3, 2. So this is our 60-degree angle. So therefore, if this is 1, this is square root of 3, then this has to be 2. So we would say our R value is 2. And our theta is equal to, we take the whole thing, 180, and we know that this is 60 degrees. So we subtract 60 degrees from 180, and we get that theta is 120. So this is how you find the polar form of a complex number from an Argand diagram. Now, trig form. The trigonometric form is actually very easy. Once we have it in polar form, it just follows into a pattern. So trig form is always written as r cosine theta plus I sine theta. Well, once we have our polar form, we already know what r and theta are, so we just plug that in. So this becomes 4 cosine of 90 degrees plus I sine of 90 degrees. And that's it. That's all you have to do for trig form. First of all, what is a critical argument? A critical argument is a formal discussion critiquing the work of someone else to prove or disprove their assumptions and conclusion. Another way of saying this is you're creating an articulate argument. So you're deciding whether that person is right or wrong, and you're giving reasons why they are right or wrong. So on your activity today, you're going to be given a table that looks like this, and you're going to start creating different arguments of why these things occurred. So you're going to compare the radius of each of the blue and green values and decide how they got the red value out of it. And then you're going to look at the direction, or theta, and decide how this and this came out to be this when we combine them. So you're going to take a look at that, and you're going to make arguments of what happened and then why you think that happened. So understanding the roots of numbers. So if I were to ask you, what is the square root of 4? Most of you would say square root of 4 is 2. But we forget sometimes that there are 2 roots. Anytime we're taking the second root, there's got to be 2 roots that exist. So we have negative 2 and positive 2. Because negative 2 times negative 2 is equal to 4 as well. So we have negative 2 and positive 2 are the square roots of 4. So if I were to give you if I were to ask you what are the square roots of negative 4? Well, we know that any negative turns out to be I. So this is really 4i here. So we can take the square root of that and we get 2i. We have the square root of negative 25, which is just 5i. Square root of 17. We leave it as square root of 17 because there is no perfect square root of 17. We just pull the I out front. So it becomes I times the square root of 17. Now here we have square root of 169. Well, we know that the square root of 169 is 13, but it should be positive or negative. So this is 13 and negative 13. Then we have the cube root of negative 8. Now notice cube root, we can have a positive value because we can have negative 2 times negative 2 times negative 2, which stays negative. So here we have negative 2 as our cube root. The fourth root of 16, we should notice is 2, and it's plus or minus 2. So that means positive 2 or negative 2. So here we have the fourth root of 16 again. We know that the answer is negative 2 and positive 2. We just came up with that. But what we need to notice is there's a fourth root, which means there's got to be 4 roots, and we only have 2 of them. So here's our little meme that says, oh, how cute, he has an imaginary friend because he has the square root of negative 1 here. So the other 2 roots do exist, but they must be imaginary. So we have our 2 roots. And if we graph those on the coordinate plane, We're going to draw our circle with the radius equal to the real root, which is 2. So our radius here is 2. And we're going to cut this into 4 equal parts. So I divide 360, because a circle is 360 degrees. I divide that by the number of roots, which in this case is 4. So I have here, and then 360 divided by 4 is 90. So every 90 degrees, I should have another line. So there's my breakup. I know that this one is here. This is 2. This one here is 1, 2, but it's in the imaginary, so it's 2i. This one here is 1, 2 to the left, so this is negative 2. And this one is negative 2i. So those would be my roots for the fourth root of 16. Now what about this one? Cube root of 27. Well, I should notice that the cube root of 27 is 3, right? That's my real root, because 3 times 3 times 3 is 27. So again, draw my circle with the radius of 3. And then I cut it into 3 equal parts. So if I take 360 and divide it by 3, I get 120. So I do it every 120 degrees. So here's one, here's another one, and then another 120 degrees is here. And then I'm going to figure out where these are. So this is 3. Now this one, I need to figure out what the value is. So I'm going to do that by making a triangle here. I know if this is 120, that means that 180 minus 120 is 60, so this angle is 60 degrees. So I know then that this is 60, and I have a 30, 60, 90 triangle that comes to the x-axis here. So I should notice then, if this is supposed to be 2, but it's actually 3, then I have to divide that. So 3 divided by 2 is 3 over 2. So that's my scale factor. So I'm going to multiply this. So this is 3 over 2 square root of 3. And this is 3 over 2. In this case, it would be negative 3 over 2. So this becomes negative 3 over 2 plus 3 over 2 square root of 3i. And here, I'm going to do the same thing. And in reality, it ends up being the exact same because this is still a 60-degree angle. So I don't have to do all the work twice. I just need to make sure that I still have the... So I just need to make sure I get my signs correct. This is negative and negative, so this would be negative 3 over 2 minus 3 over 2 square root of 3i. So these would be my 3 roots. So look at one more example. We have the 6th root of 1. Well, we know that the 6th root of 1 is 1 and negative 1. So we go ahead and draw our circle. We have our radius of 1, and we cut it into 6 equal parts. So if we notice, we take 360 and divide it by 6, and we get 60. So each one of these angles is 60 degrees. So this is 60, this is 60, 60, and 60. We know that this is 1. So this is 1, and it's supposed to be 2 based on our angle of 60 degrees. So we need to figure out, so we take 1 and divide it by 2, and we get 1/2. That's our scale factor. So this side here will be 1/2, and this here will be 1/2 square root of 3. So there's our values there. There's our root. We're going to do the same thing because this is also a 60-degree angle. All of these are 60-degree angles, so it's all going to be the same. We just got to change the signs. So this becomes negative 1/2 and plus 1/2 square root of 3i. And then this one will be negative 1, because that's just right here. Same thing here. Now it's negative and negative. So there's our negative and negative. This one will be positive and negative. So it's 1/2. And this will be minus 1/2 square root of 3i. And those would be our roots. Now closure definition. What does closure mean? Closure under an operation means a set is considered to be closed if when that operation is performed on any two elements within the set, the result is also in the set. Okay, note that this must be true for all elements in the set. If there is even one case where the result falls outside the set, then it is considered to be not closed. Okay, so let's take a look at what this means. So here's an example. We have the set of -1, 0, and 1, and want to know, is it closed under addition? So what that means is I'm going to take each of these elements, so like -1 and 1, and when I add them together, I get 0, which is in the set. So that means that the set might be closed. If for some reason, though, I end up adding two numbers together and the result is outside the set, so let's say I add something together and I get 6. Well, 6 is not in the set, so therefore it is not closed. So an example of what would make the set closed would be -1 plus 1 equals 0. Because 0 is in the set, it looks like it might be closed. Now, is there an example we can come up with that makes it out of the set? Well, if we add 1 plus 1, because we do need to include it plus itself, so 1 plus 1 equals 2. Well, 2 is not in the set, therefore the set is not closed. And again, if there's even one example of this, so it doesn't matter that this part ended up inside the set. Because this one example is out of the set, then the whole set is not closed. So now let's take a look at this infinite set here, the set S of integers, and what we want to know is it closed under addition. Now we can't use a table anymore, so we need to think of some examples of addition of integers and then try to broaden it and say, is there any way that any two integers can be added together and not be an integer? So we do some examples here, and we can see that they're still turning out to be integers. So is there any way we can add two integers together and not get an integer? So if I add any two negative integers, is there any way to get a fraction out of it? Is there any way to get a real number out of it? Is there any way to get a complex number out of it? Well, no, there's not, right? Anytime I add any two whole numbers together, I should get another whole number. So therefore, there is no way to add two integers together without getting another integer, so therefore the set is closed. Now what about this? The set S of integers closed under division. So again, we're going to think of some examples. So we have 2 divided by 1, 1 divided by 2. Notice here though, when we do 1 divided by 2, we get 1/2. Well, 1/2 is not an integer, that's a rational number. So therefore, when we do it that way, we know that it's not closed. Now, there's an easier way for us to be able to tell that this set is not closed. Because I told you last time, if we include 0 in the set, then it is never closed under division because it's undefined. So if we divide something by 0, it will always be undefined. So 0 is an integer, so if we were to divide a set by 0, it would be undefined. So therefore, that previous set would not be closed because of division by 0. Now, what if we said the set of rationals excluding 0 is closed under division? Well, again, we're going to think of some examples. So we have 1/2 divided by 1/4 is equal to 2, and -1/2 divided by 1/3. Remember, really, it's just multiplying by the reciprocal. So is there any way we're going to get something other than a rational number, other than a fraction? Well, we keep thinking of some examples, and when we keep looking, we can see that there is no way, and we did exclude 0, so we know that 0 is not an issue, so we don't have to worry about dividing by 0, so therefore, we can just look at these examples and continue to come up with more examples, and we can see that the set is actually closed because no matter what, when I divide two fractions by each other, I will always get another fraction. Let's take a look now at the Reasoning with Complex Numbers review assignment. The assignment begins with the learning goals and success criteria. If we scroll down, we can see the questions. So we're given a complex plane here, and we're asked to find 2 plus 5i. What letter corresponds with 2 plus 5i? So our real, in this case, is 2. So we're going to go to the right, 2, 1, 2. And our complex is 5, so we're going to go up 1, 2, 3, 4, 5. And we can see that we're at B. So we're going to go ahead and mark that as our answer. The answer for this one is B, right here. Now let's look at this one. It says, which transformation occurs? Z plus 3 minus 2i. Well, we know that anytime we add two complex numbers together, we're really just going to slide the complex number around. So that is just a translation. So we'll go ahead and mark that as our answer. And we'll continue to answer each of these questions until we get to the end. Once we get to the end, we'll go ahead and click Next. This will take you to your Before You Go. Go ahead and fill out your Before You Go and then submit your work on Google Classroom.